today's pre-lecture, we're going to talk a little bit more about that ICE table we looked at in the last lecture. We're also going to talk about what's called the reaction quotient. That's where we're going to start out. And we're going to very quickly talk about a BCA table, which I'll talk about more in detail in class. And then we'll also go into Le Chatelier's principle. So let's start with our reaction quotient. So a reaction quotient show is Q. It's just like K, except we're looking at non-equilibrium concentrations when we're looking at Q. So it's a number determined using the concentrations or partial pressures of the reactants and products at any point during a reaction and equilibrium. So not necessarily during, not necessarily after we've reached equilibrium. Okay, so we usually compare Q to Kc or Kp. And when we do that, that'll tell us which direction the equilibrium needs to shift in order to reach equilibrium. Okay. So if we have AA plus BB going to CC plus DD, our QC will be equal to CC DD AA BB, while our QP will be equal to pressure of C, partial pressure of D, partial pressure of A, partial pressure of B. Again, assuming all of these are gases, and assuming all of these gases or aqueous. Okay. So, if we're told a set of non-equilibrium concentrations or partial pressures, we'll put them into our Kc or Kp expression, and then we'll compare Kc or Kp. So, comparing Kc or Kp, so Q to K. If Q is less than K, that means not enough products have formed yet. To reach equilibrium. In order to achieve equilibrium, we need to shift towards products. Okay. If Q is greater than K, not enough reactants are there. To reach equilibrium. So we need to shift towards the reactant side of the equilibrium. And then the other option we have is Q is equal to K. And that means we have reached equilibrium. Okay. So let's move. And so this is just there to basically tell you what you need to do in order to reach equilibrium. And you'll be using non-equilibrium values almost always. Again, let's go back to our rice table. And we can use a rice table if we have our initial equilibrium concentrations, our initial concentrations and our K value. Without any equilibrium concentrations, we can use it to figure out our equilibrium concentrations. So we're going to use the rice table to determine equilibrium concentrations using only initial concentrations and our equilibrium constant. So before we had our initial concentrations, one equilibrium concentration, and we can use that to determine our equilibrium constant, or we can use it to determine our equilibrium concentrations and compare to our equilibrium constant. Either one of those will work. Here we're going to have our equilibrium constant, and we will have our initial concentrations, and we want to figure out all of our equilibrium concentrations. So equilibrium concentration is what we're looking for, or equilibrium partial pressures. They're not used quite as much because it's kind of a harder concept. But let's take the following data. So if we have same equation we've already looked at, H2, gas, plus I2, gas, going to 2HI, gas, being super lazy. Our initial concentrations are going to be as follows. H2 is equal to 1.000 molar. I2 2.000 molar, and then HI is 0 molar. So we start out with none of that. We also have a Kc value of 51. So we're going to take this information and determine our equilibrium concentrations. Okay, and actually, technically it's 50.5. Let's give it one more. I want to give it one more significant figure for this particular calculation. Okay, so let's do our rice table. So we have our reaction, H2 plus I2 going to 2HI We're going to put our initial concentrations in here. 1.000 molar for H2, 2.000 molar for I2, and 0 molar for HI. Our change is going to be exactly how we saw it before, minus X for our reactants, because we have to shift from reactants to products in order to reach equilibrium, and we would figure that out using our reaction quotient. So if we were to put these values into our reaction quotient, we would see that we would need to shift towards products. So we need to remove H2, we need to remove I2, and we need to produce HI, and this will give us our equilibrium of 1.000 molar minus X, 2.000 molar minus X, and then 2X. This can then go into our equilibrium expression, where 50.5, our Kc, is equal to 2X divided by 1.000 molar minus X, and then 2.000 molar minus X. Okay? Hopefully, you guys remember FOIL. So we would need to FOIL the bottom of this. If you do not remember how to do FOIL, it's first, outer, inner, last. But that doesn't make any sense. Please come see me. Okay, so we're going to do some math, and what we end up getting is, oh, sorry, this is squared at the top, because there's a 2 right there. Okay, so what we end up getting, once we do some simple math, we get 4x squared on top after we took the 2x and square it, and then we get x squared minus 3.000x plus 2.000. Okay, doing some mathematical manipulation, we get 46.5 x squared minus 151.5x plus 101.0 equals 0. Okay, so do that math. If you cannot come up with that same math, please let me know. Okay, now, hopefully, you guys also remember how to do the quadratic equation, where we have ax squared minus or plus bx plus c. If you have this, you can put it into the quadratic equation, where x is equal to negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Okay, so we're going to put the terms in, the values for a, b, and c into here. Again, if this is not making sense, please come see me, because we will be using the quadratic equation quite a lot. So we have negative 151.5 plus or minus negative 151.5 squared minus 4 times by 46.5 times by 101.0. This is all going to be divided by 2 times by 46.5. And again, I took these values. 46.5 was A, 151 or negative 151.5 was B, 101.0 was C. Put them into my quadratic equation, and once I solve for my quadratic equation, I'm going to get two values, because there is a plus or minus here. So I'm going to add it together, then subtract it, and I will get 2.323 or 0.935. We're going to be subtracting this value from our initial concentration. So if we were to subtract 2.323 from 1.000 or 2.000, we get a negative concentration, which is not possible. So x must equal 0.935. Usually when you solve for x, you're going to get two values, One will make sense, one will not. So just keep that in mind. Okay, now we can go back and put these concentrations in. So our H2 is equal to 1.000 molar minus 0.935 molar, giving us 0.065 molar. Our I2 is 2.000 molar minus 0.935 molar, giving us 1.065 molar. And then our HI is equal to 2 times by 0.935 molar, giving us 1.87 molar. We then can put these equilibrium concentrations in and make sure that it's similar to our Kc value that we got. So Kc is equal to 1.87 squared divided by 0.065 smaller molar times by 1.065 molar, and we get 51, which with two significant figures was the number that we got. So this value is very similar, so we've done good. Yay! Okay. I also wanted to, another thing you guys are going to be seeing in lab is something called a BCA table. So I wanted to hit on this real quick. A BCA, B is before, C is change, A is after. Original, I know. Your ICE table, or RICE table, however you want to look at it, is going to use molarity. Our BCA table uses moles. So RICE table is for equilibrium expressions or for equilibrium processes. While BCA is for stoichiometry. So if we have the reaction NaOH plus HCl goes to H2O plus NaCl. If we are given initial amounts, so if we have NaOH equal 2.50 moles, HCl equal 4.85 moles, and we have no starting water or sodium chloride, we can use our BCA table just like we used our RICE table. So let's go ahead and do this. So before, we have 2.50 moles and 4.85 moles with 0 here, 0 here. Our change, same thing. We're going to use stoichiometry. So minus x plus x plus x. And after, we're going to have 2.50 minus x, 4.85 minus x, and then we'll have x and x. Okay? Now, this right here is our limiting. It's in the smaller quantities. So x is going to equal our limiting reagent. So 2.50 moles. So we take for NaOH 2.50 minus 2.50 gives us 0 moles at the end. For HCl, 4.85 minus 2.50 gives us 2.35 moles. And then for our H2O and our NaCl, we're going to have 0 plus 2.50 and that is how you use a BCA table. Pretty straightforward and simple. Okay, last thing we're going to look at today is called Le Chatelier's principle. And Le Chatelier's principle basically tells us what happens as we disturb an equilibrium. So if we have a process that's at equilibrium, if we do something to stress it out, what will occur? So if we have a system at equilibrium, and it is disturbed, by a stress placed on it, and our stresses include change in temp, change in pressure, change in component concentration. Le Chatelier's principle basically tells us which way the system will shift at its equilibrium position to counter effect the stressor or disturbance. Okay, so let's look at each of these. So changing concentration. I'll go much more in detail on this in class, but changing concentration, we're going to add or remove a substance within the equilibrium expression or equilibrium reaction. And doing so will shift our equilibrium to use up or produce more of the substance. So if we add a substance, the equilibrium will shift away from that substance. So if we add extra product in, it'll shift towards reactants. Add extra reactant in, it'll shift towards products. Okay, if we remove a substance, the equilibrium will shift towards that substance. So if we remove a reactant, we'll move towards reactants. If we remove a product, we'll move towards products. Okay. Changing our pressure. When we do this, we change volume. Right? If we increase pressure, we decrease volume, and vice versa. So if we increase our pressure, or decreased volume, we're going to shift towards the side of the reaction with fewer moles of gas. And then decreasing pressure will have the opposite effect. Okay, changing our temperature. Change temperature, increasing or decreasing our temperature, depends on if we have an endothermic or exothermic process. For an endothermic process, so something that requires heat, when we increase temp, the equilibrium will shift towards products. That's because heat is considered a reactant, right? So as you increase, you're going to shift away from the reactant towards the product. And then decrease temperature. Shift towards reactants. Okay. For an exothermic process, it's going to be the opposite. With an exothermic process, heat is produced, so we consider it a product. So as a product, if we increase our temperature, we want to shift away from products towards reactants. A decrease in temperature, we're going to shift towards products. Okay? So that is everything for chapter 15. We are done. See you guys later.